What are the challenges of debugging RTOS in embedded C? Imagine trying to fix a complex machine that runs dozens of parts at the same time, all moving in different directions. That's what debugging a real-time operating system in embedded C feels like. These systems run multiple tasks or threads simultaneously, which makes finding problems tricky. One big challenge is timing issues. Tasks can race against each other, leading to unpredictable bugs that only show up under specific conditions. Sometimes, two tasks might access the same resource without proper coordination, causing race conditions. Deadlocks can happen when tasks wait forever for each other to release resources, freezing the system. Priority inversion is another problem, where a high-priority task gets blocked by a lower-priority one holding a needed resource, risking critical delays. Another hurdle is visibility. Traditional debugging tools often fall short because they don't understand RTOS-specific objects like tasks, semaphores, or message queues. Without RTOS-aware tools, it's hard to see what each task is doing or how resources are being used at any moment. Some advanced tools can trace task execution and system events, but they are still developing and may not catch every subtle issue. Embedded systems usually have limited memory, processing power, and storage. Running heavy debugging tools can slow down the system or even cause failures. Detecting memory problems like stack overflows or heap corruption is especially difficult because each task has its own stack, and corruption can cause random, hard-to-predict failures. Timing constraints add another layer of difficulty. Since RTOS systems must meet strict deadlines, pausing or slowing down the system during debugging can cause missed deadlines and hide real problems. Non-intrusive debugging methods like streaming debug data are essential here. Using high-speed data transfer tools allows you to monitor the system without affecting its timing. Many embedded systems operate in remote or inaccessible locations, making physical access for debugging impossible. Remote debugging tools and logging systems become vital to diagnose issues without being on site. Understanding the internal workings of the RTOS itself is often necessary. Bugs like task priority corruption or semaphore mishandling requiring deep knowledge of both the RTOS code and the application. This means debugging can involve analyzing complex internal data structures and system states. These challenges are common in safety-critical areas like automotive control systems, industrial automation, and medical devices. A failure to debug properly can lead to safety hazards or costly downtime. That's why using RTOS-aware debugging tools, non-intrusive data collection methods, and having a good grasp of both the RTOS and embedded hardware are key to solving these issues efficiently. Debugging RTOS in embedded C is about managing concurrency, overcoming limited visibility, respecting real-time constraints, and dealing with deployment hurdles. It's a puzzle that needs the right tools and knowledge to piece together successfully.